Hello and welcome. My name is Alexandra, and today we are going to talk about the BCS theory of superconductivity. So, what is superconductivity? Superconductivity is the set of physical properties observed in certain materials wherein electrical resistance vanishes and from which magnetic flux fields are expelled. Any materials exhibiting these properties is a superconductor. We'll dive further into this in a moment. Before we go on, I'll briefly summarize the properties of superconductors, which we will discuss in the presentation. Properties include zero resistivity at low temperatures, high conductivity, the superconducting state can be destroyed by a strong enough magnetic field, magnetic flux is ejected in the presence of a weak magnetic field known as Meissner effect, and it's a perfect diamagnet, so dB over dt is equal to 0. Superconductivity was first discovered by Oens in 1911. In the spring of 1911, Oens began his studies of electrical conductivity of metals at low temperature. Physicists at the time knew that resistance generally dropped as a sample was cooled, but they had no idea what happened when the temperature reached the extreme lows near absolute zero. Some had hypothesized that resistance would continue dropping slowly, finally reaching zero when the temperature reached zero. Others believed resistance would level off at some constant value. Still, others, including Lord Kelvin, believed that near absolute zero electrons would essentially freeze into place and resistance would become infinite, while Oens intended to resolve the question. Believing that any impurities in a metal would spoil his results, Oens chose mercury for his studies because he could produce extremely pure samples of the metal. He had been working with gold at the time, but selected mercury instead, a fortunate choice since had he stuck with gold, he would have not discovered superconductivity. He cooled mercury down to 4.2 degrees Kelvin and discovered that its resistance decreased slowly, as you would expect for any particular conductor. But suddenly, it plummeted to zero resistance at 4.2 degrees Kelvin. This is now known as the critical temperature. He couldn't explain that at the time, but certainly he was the first to really discover superconductivity. To help us better understand the issue with superconductivity, let's have a look at the graph of two variables involved in superconductivity. The first thing is temperature, we put on the x-axis, and the second we're going to look at resistance in ohms. Now, what happens to the material of a superconductor as it cools? You should remember that resistance is determined by a number of variables. Initial resistance, R naught, resistivity, which is alpha, and temperature. Focusing on temperature, what happens, of course, as we understand the expectation, is that as a material cools, we're going to expect that the temperature causes the resistance to decrease, and it will decrease at a constant rate. But the expectation is that it will never actually reach zero resistance. Now, why is that? Well, two things determine the material's resistance. Number one is that the atoms are vibrating in the material, and they are causing the electrons to be slowed down. It's like trying to run through a room with punching bags that are moving in random directions. It's going to slow you down, lowering your conductivity. And when you're colliding with rogue punching bags along the way, you're transferring energy to them, causing them to vibrate more violently. And number two, there are also some impurities in the material, and those impurities will always be there regardless of the temperature. So the expectation is that those impurities will still contribute some resistance, and you're never going to get really complete superconductivity based on this because you'll never get rid of these impurities. But what do we actually see? We see that as we decrease temperature, there is a decrease in resistance, but then suddenly at a value not 0 Kelvin, the actual resistance drops to 0, and we call this the critical temperature. And that critical temperature is the temperature where the material ceases to be an ordinary conductor and becomes a superconductor. Now that's really weird because, first of all, the actual resistance drops to zero at non-zero Kelvin, and secondly, it seems to ignore the whole issue of impurities in the first place. Having been in delicate health for much of his life, Owens died in 1926. For decades after his initial discovery, no one can explain how the effect worked. Owens himself had believed the quantum mechanics would explain the effect, but he wasn't able to produce a theory. Finally, in 1957, Bardeen, Cooper, and Schrieffer came up with a successful theory to explain superconductivity, which will be later known as the BCS theory of superconductivity, which earned them a Nobel Prize in 1972. Their theory was based on the fundamental theorem, which states that for a system of many electrons at small t, any weak attraction, no matter how small it is, can bind two electrons together, forming a Cooper pair. Okay, it's actually more like this. At very low temperatures, the lattice vibrations slow down, and these vibrations and impurities no longer have an effect on the motion of the electron. The electron is repelled from other electrons due to their negative charge, but it also attracts the positive ions that make up the rigid lattice of the metal. This attraction distorts the ion lattice, moving the ions slightly toward the electron, increasing the positive charge density of the lattice in the vicinity. This positive charge can attract other electrons at long distances. The attraction between the electrons is due to the displaced ions that can overcome the electron's repulsion due to their negative charge and cause them to pair up. The distance is usually greater than the average inter-electron distance, so that many Cooper pairs can occupy the same space. Electrons have spin 1/2, so they are fermions, but the total spin of a Cooper pair is integer 0 or 1, so it is a composite boson. This means the wave functions are symmetric under particle interchange. Therefore, unlike electrons, multiple Cooper pairs are allowed to be in the same quantum state, which is responsible for the phenomena of superconductivity. Once the Cooper pairs are formed, the lattice no longer has enough thermal energy to break the bond between the electrons in the Cooper pair. This is how the pair can carry the current through the metal with no resistance. Diving a little deeper, the BCS theory predicts a band gap of E is equal to 7/2 kTc, where Tc is the critical temperature for the superconductor. For temperatures such that the thermal energy is less than the band gap, the material exhibits zero resistivity. The reduction of the energy gap as you approach the critical temperature can be taken as an indication that the charge carriers have some sort of collective nature. That is, the charge carriers must consist of at least two things which are bound together, and the binding energy is weakening as you approach the critical temperature. Above the critical temperature, such collections do not exist, and normal resistivity prevails. This coupling is viewed as an exchange of phonons, being the quanta of lattice vibration energy. It's quite remarkable that an electrical phenomena like the transition of zero resistivity should involve a purely mechanical property of the lattice. Since a change in the critical temperature involves a change in the energy environment associated with the superconducting transition, this suggests that part of the energy is being used to move the atoms of the lattice, since the energy depends upon the mass of the lattice. This indicates that lattice vibrations are part of the superconducting process. This evidence supported the BCS theory of lattice coupling of electron pairs. As strange as such an interaction seems, it's experimentally supported by what is known as the isotope effect and the evidence for a condensation to a boson-like state at the critical temperature for superconductivity. The isotope effect is the experimental observation that for a given superconductivity material, the critical temperature is inversely proportional to the mass of the isotope used in the material. As you see in the equation where we have mass to the power of the isotope effect coefficient multiplied by the critical temperature equals some constant. This dependence of the critical temperature for superconductivity upon isotopic mass was the first direct evidence for the interaction between the electrons and the lattice. Historically, the isotope effect played a major role in unraveling the questions related to the origin of the effective attractive interaction between charge carriers, which leads to the superconducting state. The theoretical and experimental discovery of the isotope effect of critical temperature in mercury pointed towards the contribution of lattice dynamics to the instability of the normal state. Since then, the isotope effect has often been considered as a measure of the contribution of phonons to the pairing mechanism. The choice of isotope ordinarily has little effect on the electrical properties of a material, but does affect the frequency of lattice vibrations. This effect suggests that superconductivity is related to vibrations of the lattice. This is incorporated into the BCS theory, where lattice vibrations yield the binding energy of the electrons in a Cooper pair, as described in the previous slides. Finally, the BCS theory correctly predicts the Meissner effect, which is the expulsion of a magnetic field from the superconductor and the variation of the penetration depth to the extent of the screening currents flowing below the metal surface with the temperature. It also describes the variation of the critical magnetic field, above which the superconductor can no longer expel the field, but becomes normal conducting with temperature. One of the most well-known demonstrations of the Meissner effect is its ability to make a magnet levitate above a superconductor. The cause behind this phenomena is more complex than just magnetic repulsion. So if you see on this figure on the right, you have the material which allows magnetic field lines to penetrate it, and then you have the material on the right side. When temperature is lower than the critical temperature, it expels these magnetic field lines. Above the critical temperature, a superconductor has no notable effect when a magnetic field is applied, as a magnetic field is able to pass through the superconductor unhindered. If the superconductor is below its critical temperature, the applied magnetic field is expelled from the inside of the superconductor and bent around it, as seen in the previous slide. These magnetic fields are expelled because under the influence of a magnetic field, surface currents that flow without resistance develop to create magnetization within the superconductor. This magnetization is equal and opposite to the magnetic field, resulting in canceling out the magnetic field everywhere within the superconductor. This results in the superconductor having a magnetic susceptibility of -1, meaning it exhibits perfect diamagnetism. While many materials exhibit some small amount of diamagnetism, superconductors are strongly diamagnetic. Since diamagnetics have a magnetization that opposes any applied magnetic field, the superconductor is repelled by the magnetic field. When a magnet is placed above a superconductor, the repelling force can be stronger than gravity, allowing the magnet to levitate above the superconductor. This is not an entirely stable configuration, giving the magnet the freedom to spin above the superconductor while it tries to orient its magnetic poles. If the magnetic field is removed or the superconductor raises above the critical temperature, the surface currents and magnetization disappear, and the magnet will no longer levitate. To summarize the implications of the BCS theory, the theory is able to give an approximation for the quantum mechanical many-body state of the system of attractively interacting electrons inside a metal. The BCS theory gives an expression that shows how the gap grows with the strength of the attractive interaction of the normal phase single particle density of states at the Fermi level. The BCS theory also reproduces the isotope effect. It also correctly predicts the Meissner effect. It also describes the variation of the critical magnetic field above which the superconductor can no longer expel the fields, but becomes normal conducting with temperature.